Now we apply the above determinant theorem and in general the theory of alternating forms to this specific vector space, the standard vector space k power n, or also we will write k power I, where I has cardinality n, or when I is specifically n star n. This is a standard vector space and we have a standard basis E1 to En, standard basis of k power n. And remember that we are writing these basis elements as the column vectors. So Ej is the column delta Ij, where I is varying in I. It is a column where jth position in that column is 1 and everywhere else it is 0. And corresponding to this standard basis, we will have an alternating form which we have denoted by delta E. This is an element in alt n k power n. This is called a standard determinant function. On k power n. Everything is standard because it is with respect to the given coordinate system. Okay, and what we have seen is if I take x1 to xn column vectors in k power n, column vectors, arbitrary n column vectors, then we have seen delta E evaluated on this tuple x1 to xn is nothing but determinant of the coefficient matrix A. What is A? A is the coefficient matrix Aij. This is in MnK, and these Aij's are determined by the equations xj equal to summation Aij Ei. I is from 1 to n and j is from 1 to n. So these equations define this matrix A, and delta E evaluated on this column x1 to xn tuple is determinant A. And also we have seen this is nothing but, this is the definition of the determinant actually. So this is nothing but summation is running over sigma, permutations of n letters, sine of sigma, and then the product is running from j equal to 1 to n, A sigma j j. This is the determinant. This is how we define the determinant of a matrix, square matrix. You take the matrix, look at its columns x1 to xn, write columns in terms of the standard basis, take the coefficient matrix and look at this formula on the right side. That is called the determinant. And we have also seen that with this definition of determinant of a matrix, we also know that this formula, this sum sigma in Sn, sine sigma, product j is from 1 to n, A sigma j comma j. This, when I instead of sigma I write sigma inverse in the sum changes to, now I will without loss I will write the same sigma later, sigma in Sn, sign of the inverse and sign is original permutation is same. So this is same as this. So if you want write like this, sigma inverse here, then the product is now running from I equal to 1 to n, A sigma inverse I comma I. But then when I switch to this, what will happen is, this is sigma in Sn, or this sign is sigma in Sn here. Sn sine of sigma, product I is from 1 to n, ai sigma I. So this is by definition the determinant of the transpose, because the indices have changed. This is the, so that means we have defined a map det. Think of det as a map from mnk to k. Given any matrix A, map it to its determinant, and we will study the properties of this map. So for example, I want to show that this map preserves the multiplication. Also this map also characterize the invertible matrices. So we have some couple of basic things to be proved, the following. So first of all, I want to note what happens when you change a basis of the determinant functions. So let us write it as a theorem. Suppose I have two basis tuples, V is one basis tuple, Vi, I in I, and another is V prime, which is numbered by the same indexing set Vi, because we know any two bases of a vector space have the same number of elements. Two k bases of a finite dimensional vector space V, k vector space V, the dimension of V is cardinality I, which let us put it n. Then we know we have two determinant functions, one corresponding to V, delta V, and another one corresponding to V prime. Both are non-zero because this evaluated at V1 to Vn is 1, this evaluated at V1 prime, V2 prime, etc. is, so both these are non-zero elements in the vector space ALT NV. So therefore one must be a scalar multiple of the other, and then I want to find what scalar multiple. So that scalar multiple I want to find. So that is, I want to write delta V prime as some scalar multiple. This is somebody in K, I will calculate that, times delta V prime. That means this is a scalar multiple of this, not V prime V. So I want to find what is that scalar. So obviously how will the scalar will come out from? Scalar will come out from so called a transition matrix. So let me write the answer here. So this answer is determinant of B, where B is the transition matrix from V prime to V of ID. If you remember this is nothing but Bij, and Bij, this is a matrix Mnk, and these Bij's are defined by the equation Vj equals summation Bij Vi prime. I is from 1 to n and j is 1 to n. So when you write a basis vectors in the basis V in terms of the basis vectors in V prime, then you get coefficients, and that is this coefficient matrix. It is called a transition matrix from V prime to V, because upper index is always written from where it is, and these are in terms of this, you see, because of this. Okay, so let us prove this formula. This is very easy. Proof is just only one line. You just have to evaluate both sides. See, these are both are alternating maps, and they are uniquely determined by the basis values, and we know that delta V prime, left hand side, delta V prime evaluated at Vi prime I in I is 1 to n, this is 1. That is how this is the a determinant function corresponding to this basis, but this is equal to, now just plug it, no, I want to compute, sorry, I want to compute, I want to compute left side delta V prime on the basis V1 to Vn. This side is what? If I want to evaluate delta V1 to Vn, this is 1, and I have to prove that this is, so enough to note this actually. We have to prove this equality. Once I prove this equality, this equation is clear, because evaluating both sides on V1 to Vn will give you this, and it is uniquely determined by this tuple. So, and this is what? This is okay. So, how do you do this? This is just substitute each Vj here and expand that generalized distributive law, and then you will get this value, that is summation running over sigma in Sn sin sigma product is from j equal to 1 to n b sigma j j, but this was precisely the definition of this determinant. So, this is clear, and this equality we know from the general distributive law, therefore, this is clear, and therefore, this equality is clear. Everything is very easy. And now, if I want to shift this constant to the other side, I know this is B is a transition matrix of the basis, from the basis V prime to V, but then it has to be, it is an invertible matrix, because it is a transition matrix. We have proved that it is in GLNK. Therefore, also we could write the same equation as we could have written as delta V prime, no, delta V equals det B inverse times delta V prime. So, I want to specifically note this in a form of theorem. So, let me write this as a theorem, which is very often used. In fact, many people take this as a definition, which is not very correct. So, let delta be arbitrary alternating form on V, be arbitrary alternating or arbitrary determinant function. On V, that simply means this cardinality of I is equal to dimension V, and delta is alternating multilinear, and then a tuple xi is arbitrary tuple in V power I, is a k basis of V if and only if delta evaluated at the tuple xi is non-zero. This is, in fact, this is one way to prove that any two bases of a finite dimensional vector space have the same cardinality. That is, namely, the cardinality of, the smallest cardinality where there is a non-zero alternating form. Okay. Already we have, so proof. See, they are correct in number. So, I only have to prove either they are linearly independent or a base or a generating system, because the cardinality, since cardinality of I equal to dimension it is enough to prove that the tuple xi is linearly independent, if and only if delta of this xi I in I is non-zero. But this is what we proved it earlier, because this way definitely we have proved it. We have proved a contrapositive. Actually we have proved that if the tuple is linearly dependent, then the delta of that tuple is 0, and otherwise you see this delta function, if it is a basis, this way, if it is a basis, then delta must be some scalar multiple of delta x if it is a basis, where A is actually delta of xi. So, if A is non-zero, that is this is non-zero, then it is a multiple, it is a non-zero multiple of this determinant function, so which is non-zero. Okay, so this is the proof. So then in the corollary in the matrix format, suppose you have a matrix A, square matrix, then A belongs to GLN K if and only if determinant of A is non-zero. So, proof, note that, so the definition in GLNK means A is invertible, A is invertible if and only if rank of A is n, that is if and only if columns of A are linearly independent over K, that is if and only if det A, which is by definition delta, standard delta function evaluated at the columns x1 to xn, is non-zero. So, where x1 to xn are columns of A, these are in K power n. So, that I just want to make one very important comment here. Many people take this as a definition of GLNK. That should not be. This is a theorem which characterizes invertible matrices by means of the scalar being 0 or not 0. So, this is very important, because for example, when you pass on from in general case from a field to arbitrary commutative ring, then it's very important. For example, when you take K equal to ring of integers and you consider matrices over ring of integers, and which matrices are invertible are not the matrices whose determinant is a non-zero integer, but matrices whose determinant is actually a unit in Z. So, the only possibility is 1 and minus 1. So, a matrix A in MnZ is invertible if and only if determinant of A is either plus 1 or minus 1. So, even for example, if we take 2 by 2 matrix, say 1 and 2 and 0 0 here, this diagonal matrix, the determinant is 2, and this matrix does not have inverse in Z with integers entries in Z. It has 1 over 2 will come in the in the denominator of the entries, where the matrix does not have integer entries, it has only the rational entries. So, in that sense this is very important to write in this way, because for generalization this will come in handy. Okay. So, now the last observation here, even the rank we can compute by using determinant. So, that is known as minor criterion. For computation of rank of matrices. So, first let me recall what a minor is. So, when you have a matrix, now this matrix, now you can take a general matrix. A is a matrix with m rows and n columns, and let us write this as A I J. So, I is running from 1 to m and j is running from 1 to n. If I fix any r, which is, so rank cannot be more than the minimum, and for any r which is less equal to the minimum, I want to choose r rows and r columns and form a sub matrix of the given matrix A. So, that I will write it as, so suppose I choose the rows I1 to IR rows and J1 to JR columns. So, I only take those entries from these rows and these columns. So, in that matrix I want to denote by I1 to IR, J1 to JR, J1 to JR. This is the sub matrix of A, which consists of I1 to IR rows and J1 to JR columns. And J1 to JR columns. So, that is also you can write it. So, the first row is I1th row. So, AI1, first column is J1. So, AI1 J1, AI1 row is same, column is J2 and so on. So, AI1 JR, and similarly I2, I3, IR J1, IR J2 and IR JR. Actually, if you notice, lot of energy goes in deciding what is the matrix. It is better to deal with the linear maps. Okay, so this is called R minor of A. Determinant of this, determinant of, it is a square matrix now. I1, IR, J1, JR. This determinant is called a R by R cross R minor of the matrix A. There are many R cross R minors of A. See, for example, even if you take 3 by 3 matrix or 4 by 3 matrix, this is 4 rows and 3 columns. If you want 2 by 2 minors, it can be this, or it can be this, or it can be this column with this column, and so on. There are so many possibilities. So, there are many R cross R minors of the matrix. Now, the criterion says for rank. So, let A be a matrix with m rows and n columns, and R is a rank of A. Then obviously we know this R is smaller or equal to minimum of m comma n. Then for all S bigger than R, S cross S minors of A are 0. All S cross S minor where S is bigger than R, they are all 0, and there exist at least one R cross R minor of A is non-zero, then the rank is R. So, proof. This is, I will not give the details, but I will just remind you that, remember, for doing the rank, we have proved that rank of A, the definition was the column rank, that is the maximum number of columns which are linearly independent, and we have proved that by going to the transpose, we have proved that this is same as the row rank. So, use this fact to check this. This is very easy to check. Okay. Okay. Now, I will also want to make one remark which I do not remember if I made it earlier, but it is very important. Suppose we have a matrix A, M cross N matrix, M n K matrix, and K is a field, and suppose I enlarge the field L. L is a, so L over K, L is a field extension of K. Then obviously I can also consider this as a matrix. This is contained in M, M, N, L. It is a matrix with entries in L also. Typically rational matrix you can think as a real matrix, or rational matrix you can think as a complex matrix. Then rank of A as a consider as a K matrix, and rank of L consider as a matrix in matrix over L. These two ranks are same. This is very, very important. These are already we have applied these in a Gauss elimination also. When I said that if you have a system of linear equations with rational coefficients, if it has a complex solution, does it have a rational solution? Answer is yes, it has a rational solution also. So, this okay. So, then next time I will consider how do we make computation with the determinant. So, next time we will do computational rules for determinant, where I will also prove we will also consider adjoint of a matrix and determinant adjoint formula and so on. So, next time. Thank you.